Hello. In this video, we are going to investigate the projectile of an object with air resistance. Okay, imagine that you have an object here. It's a point object, so it doesn't have rotation or any shape. It's at one point, and it has a velocity v. Then this velocity can be projected to vx and vy. Here's a free body diagram, so there are forces. We know that the air resistance force is opposite the velocity. So if the velocity is like this in a dashed line, the air resistance will be like this in the opposite direction. And we have a coefficient called c that multiplied by b, and that is equal to the force coming from the air. There is another force involved here, which is the weight. So it's mg. M is the mass of the projectile, and g is the gravity. So just to be complete, we write here the x and y coordinate system. The y is vertical, the x is horizontal. All right, so using the Newton's second law, we write the acceleration times the mass equal to the force, right? So the total force here is the weight minus the force coming from the air. All right, and we know that the gravity is in y direction, and the gravity is in y direction, and it's negative g is downwards, and there is no gravity at x direction. We can change this based on our coordinate system, but we are not going to complicate to make our analysis complicated. All right. Okay, so the approach that I'm going to use today is to do a scale analysis, or to non-dimensionalize our equation first and then go forward. It makes the calculation easier, and also it makes the plotting easier, that we will talk about in the next video. Okay, to non-dimensionalize the equation, we need some scales, some typical scales. So for the velocity, both x and y direction, we use similar factor, u. For time, we put tau. We don't know it yet. To non-dimensionalize this, the first term in the right-hand side, mg, we need to non-dimensionalize the vector g. We know that the value of the gravity, the magnitude of the gravity is g. Gravitational acceleration is g, so we non-dimensionalize that using the known value. So this will be our new dimensionless quantities that we need to substitute in our original equation. So to do so, we can substitute v, this is a vector, v with u, v star. V star is non-dimensionalized. It doesn't have any unit or any dimension. It's a number. So, however, this u has a unit. Okay. So, if you do that, we will get to this equation. So replace this v with u v star, t with tau t star, g with g star, And again here we have v, we put u v star. All right. So now this is our new equation, and I can rearrange it, keep this this derivative on the left hand side, and put the coefficients to the right hand side, and have the equation here. Okay, and so we want all these terms to be significant. So here comes the scale analysis. So we want to have this term and this term in our analysis. We don't want any of them to be negligible in respect to the other, right? So we know that we non-dimensionalize this v, t, g, and the other v here, which is the same as the first one. So based on the scaling rules that we can talk about it later in another video, if each of these coefficients, the total coefficients, be in order of 1, then the summation of them will be in the order in order of 1, in the same order, and then the left hand side also will have the same order. So therefore we want this guy here has the order of 1, so we show it this way. Order of this is tilde is 1, and it's not equal, it's in the order of 1, and then tau should be in order of u over g. Okay, so just keep this one. And for the second term, we do the same thing. We want to keep this term as well, equally significant, and then c tau over m need to have in the order of 1, and then u should be the order of mg over c. So by doing this, we make a relationship, or find a relationship between the typical scales, so we can actually substitute them, and we use them in our analysis further. So if we have u in the same order as mg over c, and we replace it here, and we have tau in the same order of u over g, and we replace it in our non-dimensional equation, we'll see that the terms, the coefficient vanish, cancel out each other. So we will have this non-dimensionalized equation, which is much more simpler than the previous one. And it doesn't have any coefficient. Everything is in the same order and order of significance, and we can move on. We can solve this equation, and at the end we replace the v star, g star, and t star with v, g, and t, and then we will have the dimensional solution. Okay, so from now on we work with non-dimensionalized or dimensionless equation and quantities. So to have a vector equation satisfied, you need to satisfy all the components, right? So they need basically this vector equation we have in a two-dimensional space that has x and y. Is basically a set of two equations. So it has x component and it has a y component. So we focus on x component first. In the x component, you can see here subscript x. So dvx star over dt star is equal to minus vx star. So from now on, I keep saying star for simplification, but everything here is dimensionless. When I say V, I mean V star, all right? But it's all written in an asterisk. So here we have dvx over vx equal to minus vt in a dimensionless form. And now, if we take integral from both sides, we will have the natural logarithm of vx star equal to, okay, and the bounds are from vx0, consistent with the rest, v0x, so it's the initial velocity in the x direction and not dimensionless, and until now, which is vx. Okay, stop. And for here, you have from 0 all the way to t star. So this becomes and I'm sure you know the rule for this natural logarithm, so I just quickly go to the end, and then you'll have this vx star over v0x star, right? And the other side is pretty simple. So the result will be here, it's written here. So it's a natural logarithm of vx star that I wrote it, I solved it here, and then I can write the exponential of both sides. So operate to apply the exponential operation, and then this will become vx star equal to, so just write it here, it's easier to understand. So if I put this exponential operation to both sides, it is exponential of this guy here that we wrote. And then this becomes this guy. Right, the exponential of the natural logarithm is zero, that they cancel out each other. And then for the other side, we have exponential of minus t star. Right? So then we rearrange it. So just get rid of these things to have nice and tidier board. Okay, so we will have this one. Perfect. So then we can substitute this v0x star with this value. So this is v0x star, v naught x star, or v naught star x direction, and then our vx, the velocity component at x direction, is written here. So this is what we wanted at x direction. Cool. So now we move on and we go to calculate the velocity direction at y, the velocity component at y direction. Again, we start with the dimensionless equation. Now we have this g. For the previous one, the g component at x direction was 0, but here the g component at y direction is minus 1. It's dimensionless, and we non-dimensionalize it with g, so we have minus 1 here. So the equation turns to be derivative of vy n star equal to minus 1 minus vy star. Okay? So what we can do is to keep this minus 1 here and this, and we take this fella to denominator and take this fella to here, right? And then we will get something like this. So what we do here is we take integral from both sides. It's easy, we can do this, and for the right hand side it's pretty easy. This becomes b minus. This becomes minus t, and for the left hand side, let me just write it here like that. So we have this integral dv1 star over 1 plus dy star, and this is equal to the natural logarithm of 1 plus b star, right? And so we want to start from the bounds are y of 0 star or not y star, and then y star. So this one bounds come here, so this becomes, so it's minus this one minus the same thing, but we substitute v naught y star, and then according to the laws of natural logarithms or logarithm laws, we will have this right. So then for the right hand side we have minus t star. Again we apply exponential operator, and then we will get rid of this natural logarithm, and then on the right hand side we have e to the minus t star, and then we multiply this fella to both sides when we got rid of this ln, and we will have what's at the end. It will be a good practice if you want to derive this yourself. Okay, so now we have calculated so far the velocity at x direction in the dimensionless form and y direction, right? So we have a velocity of a projectile in a situation in a 2D plane with air resistance, right? But now we want to find out the path of that object. So we want to know how that moves, not how fast that moves. So how fast that moves is fine. We already calculated, and now we want to go one step further and find out how that projectile under influence of the air resistance moves. Okay. The next step is to write the relationship between the velocity and the coordination, the location, the position, right? So we know that the velocity in x direction is derivative of x, the distance, the movement, the length of the movement, right? The distance that it goes with respect to t, respect to time. So we want to use the same factors, same typical scales to write a dimensionless equation. So Vx is again like before, it's u Vx star. Dx we write L dx star, we don't know L yet, right? And dt is tau dt star. We know t, we know tau, actually we calculated it above, right? And we use that. So after rearranging this equation, we will see Vx star is equal to L over U tau dx over dt in dimensionless form. So again, we want this to be 1, so it's L. We want to be equal to, or almost equal to tau u. We know that tau is equal to u over g. If you check the dimensions or units of this fellow, it should have the same right hand side and left hand side, right? So when you do this, L becomes u squared over g, and then you have u is equal to mg over c, and then if we substitute, we will have L, which is the dimension length, which is the typical scale for the length, equal to this fellow, m squared g over c squared. All right. We did it for the x, but it's the same for the y, so we assume that the length scale is the same for both of them. So it means that the movement in x direction and y direction have the same, typically have the same scales, which is correct. It's not always this way in all problems, but in this problem we have this this situation. Okay, so now we do the final part of our calculation. We have this one. This is the x star. I wrote it in a form that it's according to its definition. So it's the derivative of x with respect to t in dimensionless form, and this is what we have. We will calculate the path, and then what we do, we keep dx on the left hand side, dt, we multiply both sides to dt star, and we have it on the right hand side, and we have this one. We do the integration. This is pretty simple. This becomes delta x star, and then we will have from t0, which I put 0, and to t star, and then the result will be v naught star cosine of theta. The theta here is the angle of the initial velocity, right? So v naught star cosine of theta, and then this becomes minus t star, right? And from 0 to t star. So when it's t star, it's the same thing. When it's 0, e to the 0 to the power of 0 is actually it's equal to 1. So the result will be v naught star cosine theta 1 minus t star, right? Which I have written here. Okay, and we do the same thing in y direction. We have the y star or the t star, the derivative of y with respect to t, in the dimensionless form. We have this equation. We had calculated this above, and we start from this. Again, take so multiply both sides into dt star, and then take integration, do the integration, and then it's pretty simple. It's t, and this part, this first term on the right hand side becomes this. So I keep this one for you to practice. It's not difficult. It's very similar to what I did above, and the only difference is that we have a 1 here, and it has 2 terms in the bracket, right? Okay, so now we have all the results that we wanted to have. So we calculated the velocity of a projectile with air resistance, and we then, using the velocity, we calculated the location of that projectile, x location and y location, right? In the next video, we will write a code Python code to to plot the projectile and also to present it in a very nice and beautiful way, to make it very easier to understand how it goes. Just for the bonus part of this video, I want to show you what we can infer from this dimensionless equations, and which is pretty easier to do in a non-dimensionalized form. Okay, so quickly, imagine, just consider this y star. Okay, when it when t star is much larger than 1 minus e to the minus t star becomes it actually goes to 1, right? And then the y star is in order of, is almost equal to, it actually approaches minus t star. So when we want, now we can actually bring in the typical scales. So we can substitute the stars, these dimensionless quantities, with dimensional quantities. So what we can do is that we can write, alright. So what we can do here is to write, instead of delta y star, we write delta y over the length scale that we had above, right? And then minus t, we can write it minus t star, we can write it minus t over tau, and tau is m over c, right? Therefore, when you simplify it, it will be with the y over minus g m c over t. So it means that the effect, what we implied here is that the effect of the air resistance is significant or considerable when t star is in order of 1, right? But just now, what does this tell us? Let me calculate the terminal velocity of an object that's falling down, all right? The terminal velocity means that the object is not accelerating anymore. It's moving in a very steady velocity, right? Because of the air resistance. In the other words, the velocity, the force coming from the air is cancelling the force of the gravity, right? So you have CV equal to mg, right? So V is equal to mg over c. Look at this too. This equation number 1 and equation number 2. We realize that this term is actually V y with a negative direction, with a negative sign, right? So our scaling analysis actually told us what is the terminal velocity. So this is quite interesting that without calculating this part, we could mathematically infer that what the terminal velocity would be. All right, so I think it's good so far, and in the next video we will use Python to plot the projectile with air resistance in different situations and illustrate that. See you later.